A little bit at the connection of dynamical systems with differential equations, ordinary differential equations. Also known as ODEs. Yes.
So,
So
where is that? Yes. Yes.
it's going, I think. No?
Yes, it's good.
Yeah. So historically, ODEs come in some sense before the study of the modern theory of dynamical systems. As you know, goes back to Newton and Leibniz and hundreds of years ago. But there's a very strong connection, and it's interesting to see them connected in this way. So most of you will have done probably some course in differential equations, right? But maybe most of you have done courses in which you have to solve differential equations. Yes? So today we will try to look a little bit at what a differential equation is, a little bit at the basic theory of differential equation. So let's first start of all with the flow, which is what we were doing last week, a continuous time flow. And let's just start with an example. Okay. Of a flow where x is equal to R2, okay, and the flow, so we have our flow of t in R is given by f t of some point x0, y0, some initial condition, is equal to x0 e to the alpha t and y0 e to the beta t. And let's suppose that let me draw it here. So let me suppose that alpha is positive, so it is negative and alpha is positive. So what does this flow look like? Does it have a fixed point?
0 and 0.
0, 0 is a fixed point, right? Because this is the initial condition. If you start in the origin, this will always be 0, 0. So 0, 0 is a fixed point. Okay. What happens if you take a point here?
It accumulates to the x-axis.
That's right. So if it has x0 is equal to 0, right, then this is always 0. And y0 e to the beta t, beta is negative, so this is going to 0, this part. Yeah. Okay? So the flow, if you start with this initial condition, it is flowing down. Like this. Yes. What if you take a point here? It is going that way, right? If you take a point here, in forward time it's going to the left. This is all in forward time. Of course, the reverse happens in backward time, right? There's a kind of symmetry. If t is negative, then they will go in the opposite direction, right? So this point is kind of coming from here. In backward time, it goes back here, and so on. And this one is also going down here. Okay, what if we take a point here, x0, y0, a generic point? That's right, okay, so it's easy. It is going, in fact, the coordinates follow exactly the coordinates of this point, right? So after some time t, this will be here xt, and this will be yt. Okay, this is equal to x0 e to the alpha t, and this will be equal to y0 e to the beta t, right? And you can see that this is in fact doing something like this. And in backward time, it is going Yes? So the flow, the orbit of the flow in the y-coordinate is getting closer and closer to 0, so it's going like this. Okay? And you can easily see the shape of all the other orbits, like they all look like this. If you take a point here, it's going like this. If you take a point here, it would be going like this, and so on. It's got this kind of picture. Hyperbolic. These are kind of hyperbolas everywhere. Okay? If you take a point that is very close to here, then it will come down very close to here and very close to here. This is the kind of picture. Okay, this is a flow. So that means that if you choose an initial condition, we have xt. So we can write this as xt yt. Okay? So in some sense, well, not in some sense, this is a function of t, right? We can think of this as a this is really, you can think of this as a function t goes to xt yt. Okay? This is a function that depends on your initial condition. Okay? But once you fix the initial condition, you have this. For t equals 0, you get x0, y0. And for all different values of t, you get xt, yt, whatever this function is. Okay? So this is a function from R to R2. In other words, it's the function that for given initial condition associates to each t the image of the position of the point after time t. So we can take the derivative of this function with respect to t. Right? What is the derivative of this function with respect to t? So xt and yt are given by this. Okay? So the derivatives how should we write this? So let's write this as z of t is this point, right? And so the derivative z dot of t is equal to, how do you calculate the derivative of this? These are the two components of this function, so we take the derivative in each component, right? The derivative will be a vector, so it's x dot of t, y dot of t, okay? The derivative with respect to t, and this is equal to what? This is the function. So alpha x0 e to the alpha t and beta x0 e to the beta t. This is the derivative. Sorry? Y0, thank you. So geometrically, so this also has two coordinates, and geometrically you probably know this vector, if we draw this vector centered in this certain point here, xt, yt, by some miracle, is actually tangent to this curve. Yeah, you know that? If you take a parameterized curve and you differentiate just like we did, this is just a parameterized curve, right? This is a curve parameterized by t in R2. We take the derivative with respect to t, we get a vector, and if you draw this vector aimed at that point, it is tangent to that curve. Okay, this is just part of calculus. It's something that's part of calculus. So at every point, we have a vector that is tangent to the curve. Yeah? At every point of every curve, of every solution. And there is, in the plane, there's a curve through every point. Right? This is clear. So I can take any point as the initial condition and I will get the curve. And clearly, if I fix a curve, I take this initial condition, I get this curve. If I take this other point on the same curve as its new initial condition, it will be different. It will look differently, but it will give the same curve. right? So of course so the whole plane is filled with these curves, right? It's kind of partition of the plane. So at every point on the plane, there's a well-defined vector, which is exactly the vector, and there's no, these curves, they never cross. Okay, in this particular case, it's obvious because we have the explicit formula for the curve. Okay, but in general, I will make this remark later. When you have a flow, the curves that correspond to the solutions to the orbits, they can never cross. Okay, it's easy to see. But so now here we have a vector at every point. Now there's an easy way to actually write this vector in terms of the point. So at this point Z, okay, this is the point Z of t. What is the vector here? Do you notice what the vector is? It actually, we can be written very easily in terms of the point, because look, here we've got alpha x0 e alpha t and beta y0 e beta t, which is the point, right? So this is just alpha xt beta yt. Actually. So, what we're saying is that this flow satisfies a remarkable property, right? That if you take a orbit of a point, then the derivative of that orbit with respect to t is always of this form at any position along the orbit. Okay, so another way to write that, we've seen this picture now. Another way to write that is that x dot t is equal to alpha xt and y dot t is equal to beta yt. If you want, that's the way to write this. Okay? And another way to write this is as a differential equation that, okay, so we can, sorry, before I write it differently, so this is just writing the equations that come from this particular observation, right? That if you have this system of equation, then you have all the tangent vectors. Now suppose that I give you at every point, a vector, so suppose that I define at each point xy in R2 a vector phi of xy equals alpha x beta y. So, because I mean here the dependence on t, I've got the dependence on t because this is the point xtyt, but really what I'm saying is that whatever this point xtyt is, the tangent vector is of the form alpha x coordinate, beta y coordinate, right? So here I am going to define this vector so I can draw at each point. So here I draw, for example, I take the point 1, 1, right? And I draw a vector that is alpha is positive, we said, so this would be alpha x, beta negative, so it would be something like this, right? And then I take another point, say here, 4, 3 here, whatever, and I define another vector that is just alpha times 4, and beta times 3 will give you something like this, okay? And at each point, I have a vector, and in fact, this list, all these vectors will look something like this. Bunch of vectors, right? Is that clear what I'm doing? I'm just putting at each point this vector here, alpha x by. Okay? I'm taking this vector, but I'm putting it based at the point xy. So the base of the vector is at the point xy. And then suppose I didn't know what I knew before, and I said, okay, now I have a bunch of vectors in the plane. Is it possible to put some curves through this plane, which at every point are tangent to the corresponding vector that is at that point? Right? And in this particular case, we have the solution here. So in this particular case, we've seen that if we draw this family of curves, so for any initial condition, you take this point here, initial condition, and you draw the curve corresponding to this, to exactly this flow, this dynamical system here, then as we have already proved, then the tangent vector at each point, for example this point here, will be exactly of the form alpha times the x coordinate of that point, beta times the x coordinate of that point, which means that at this point you will have exactly the vector alpha x by through this point. So maybe there's several ways of saying this. Maybe I should have said initially when I had the picture before, I should have said, okay, now imagine that you have drawn, so we had all the lines, all the solutions. Imagine that you draw at every point the corresponding vector, and then you pull out the lines, okay? And all you're left with is the vectors, okay? When you look at the vectors, it's not immediately obvious just by looking at them that there are these lines that go through them. All you have is a bunch of vectors that look a little bit like they're moving, you know, they're kind of pointing in this kind of direction, but it's not completely obvious. But because we have this particular formula, and we know that it comes, you know, we know that the derivatives along these lines, then we match up the curves and the vectors. Any questions?
So the converse must be small.
So the converse, sorry?
So I'm asking about the converse. So suppose we don't know this.
Exactly. So the converse is exactly the problem of differential equations. Okay, that's exactly it. So I tried to introduce them in the opposite way. So the converse is now given a vector field. So here we have a very specific vector field, and this very specific vector field can be solved. So the way you will have seen that is a variation of this, where you write x dot equals ax and y dot equals by, for example, right? This is a form in which you might have seen a differential equation, okay? And then how do you solve? You can also do this just in one dimension. Notice that this is really the two coordinates. So it's saying, in this particular case, it's very simple because the two coordinates are completely independent of each other. So if you have the differential equation, for those of you who've done the course where you solve differential equation, you know how to solve the differential equation x dot equals ax. Is this familiar? And what is the solution of this equation? Sorry?
E to the ax.
Exactly.
Yeah. Maybe sometimes.
Alpha and beta, this should have been so. Exactly. E to the alpha t or e to the beta t. Those are exactly the solutions. Okay? But why are these the solutions?
Exactly. That's my question is, so sometimes there are differential equations who has not a solution or has more than one solution for each initial condition. So
That's right, that's right. So we will look at that. That's what we're going to talk about today. Okay, so what it means to have a solution. So, so in this particular case, what this really means, right? When you solve it, what does x dot equals ax mean?
Is a fixed point of some algorithm?
Okay, let's forget about how we calculate the solution for the moment, okay? What it means is there exists some parameterized function x of t, which we have here, which satisfies this property, right? So what does a solution to this mean? It means that you're looking, what really this is saying is x of t, right? So the derivative at you want a function x of t whose derivative is equal to alpha times the position of the point x of t. That's what it really means. So every time you write, usually I think this causes a lot of confusion, the fact that the notation that is usually used for differential equations does not usually contain this t, and so it's not that obvious to understand exactly what we mean, okay? So the solution to this would be a function x of t, okay, that tells you that is x of t is a point that depends on t, so this is a function just like we have here, t into your space, whatever your space is, and x dot of t is the derivative of that function with respect to t, okay? And this is telling you that you want that relation between the derivative and the position of the point, which is exactly this, okay? That at each point, the derivative is exactly equal to alpha beta times the two coordinates of the point, okay? So how do you generalize this? So more generally, this is called a vector field. Okay, this is called a vector field. So if M, so let's for simplicity suppose that we have Rn. So let's suppose that our space is Rn. The same thing can be done as we said on manifolds, on spheres, torus, but you need a bit of differential geometry for that. And then we say that a function v from Rn to Rn is called a vector field. So this is another potential source of confusion here, because we're not going to iterate this function, right? What we're saying here is we take Rn, for example, the case r equals 2, R2, okay? And for each point of Rn, for each point xy, you define v of xy is a vector. But you think of this vector as being based at the point, right? So what this is telling you is that for each point xy, here you have a point xy, and this function is telling you, okay, at this point we're going to put this vector here. Okay? At another point we're going to put another vector. At this point we're going to put another vector. So at every point of R2, it's telling you that there's a vector. This vector may be small, may be very big, whatever. Okay? So even though we write it as Rn to Rn, this is not a discrete dynamical system. It's called a vector field. And now the question we ask, when we write it as a differential equation, we write x dot equals v of x. This is the fundamental notation for a differential equation. And a solution of this differential equation is a function x. So a solution, this is called an ordinary differential equation. In fact, this is called an autonomous, because you can have more general versions in which depends on t, but let's not talk about that for the moment. So this is an autonomous ODE, and the solution is a map or a function, is a function x from I to our space to our n, let's say in this case, which has the property that at each point such that x dot of t equals v of x of t. For all t in I, where I is some subset of I. So these are the two fundamental definitions. So if you have a differential equation here, you see you should compare it to the specific example that we had before. So v of x, so in this case x will be the coordinate xy. There's a little bit of an issue with the notation. What I mean here, of course, is the point in your space. So it could be xy or xyz, depending on how many dimensions you've got your space. And we have defined a vector field. Okay? So at each point in your space, we have a vector. Think about this specific example. Okay? In this specific example, the vector is given by this, alpha x, beta y. But you can have any function, okay, that is telling you which vector to put at every point. Now, we put this here, this vector, and then what does this formula mean? Okay, this formula means that we're looking, we would like to see if there exists some solutions to this, and a solution is a function from some t. Now, the reason I put this I is because sometimes the solution is not defined for all time. We will look at specific cases.
Such that x dot, right?
Yes, sorry, thank you. Yes, yes. So the solution is a function that has exactly this property, that if you now look at this function and how this function evolves with t, so x of t is the position of this function, right? So sometimes I put t in brackets, sometimes I put it as a subscript like I've been doing there. It means exactly the same thing. It's just the dependence on t. So if you look at the vector that is given by the vector field at that point, then the velocity of this function with respect to t is given exactly by that vector. Okay? In other words, you don't start with a flow and calculate the derivatives, which means the velocity, right, with respect to t at every point, but you're given a vector field or a velocity field, in some sense, and you say, okay, I want a system, I want a flow that just happens to have exactly this set of vectors as its velocity field at every point. Okay? Can I do that? Is the question. Okay, that is the fundamental question. So the fundamental basic question is, given such a vector field, do there exist solutions? So what I'm going to state today is a theorem that says under which conditions there exist solutions, and also we'll see some counterexamples. Yeah, in fact, let's start with the counterexamples, because sometimes there exist. So the fundamental questions are existence, uniqueness, and how big is the interval on which the solution can be defined. Okay, those are the three main questions.
And continuous flow, also important.
Sorry?
And
So the vector field will have to be continuous for their solutions to exist. Or the continuous dependence on initial conditions.
Yes.
Yes. Yes, so you also want to know things like, okay, so sometimes this problem is written as the so-called Cauchy problem. You will have seen that, right? When you specify an initial condition. So sometimes, this is sometimes written as the so-called Cauchy problem, which is written as x dot equals vx and x of 0 equals x0. So a specific initial condition. So you want, this is the general problem is given this, there exist solutions. Of course, it may be that there exist solutions at this point, so it may be that if you choose this initial condition, you can actually find a solution for this point, but maybe here you cannot. The vector field is such that you cannot do it. Okay, so this is just, the Cauchy problem is really the same thing. It's just a way of saying, okay, I actually want to know if there exists one here at this point. Okay, and the main questions are existence. So does there exist a solution with this going through that point? Uniqueness. Could there be more than one solution? And how big the solution, how long? So we will see an example in which the solution is defined on an interval of time in some sense, but not for all time. So domain of definition I. So how big is the domain of definition? Okay, so these are the three fundamental questions. So let's see some examples in which I'm not going to give any examples where this does not exist because I did not think of preparing any, but the theorem we will state at the end says that whenever this vector field is continuous, then through every point there exists a solution. It's a very standard, it's one of the classical theorems, which is actually quite remarkable when you think, in some sense, the problem, you have a kind of vector through every point here, you know, they might be going different directions, but they vary continuously, so you cannot have a vector here and immediately afterwards a vector going in completely different direction, right? So if the vector field, this function here, is continuous, then through every point there exists some solution. This is a standard theorem. But the uniqueness and the domain of definitions are much more subtle. And let's see some of the examples that show that you do not always have uniqueness and you do not always have them defined for all time. So let's look at one example, which here we have just on the real line, okay? And we have the differential equation x dot equals 3x to the 2/3. So maybe you've seen some of these examples before, because if you've done the solution of these examples. So first of all, let's think of it as a vector field, because I want to emphasize even in one dimension we have a vector field. So what does this vector field look like? Is there a fixed point for this? So first of all, is this continuous? Right? What we're saying here is that the vector field V, so V is a function from R to R, and X goes to 3x 2/3, right? So this is X dot equals V of X, where V is this function here. Okay, this is the vector field, which means that at each point we put this vector. Okay? So what vector, to be really accurate, we should put like the sign plus or minus. So we assume that the sign of this is positive when X is positive and negative when X is negative. Okay? So what is the vector at 0? 0. Okay, that's okay. We can have 0 vector. Just like, in fact, in the example I did before, I did not emphasize that, but at 0 you have a 0 vector there. Okay. What is the solution with initial condition in the 0 vector? It's just a constant equals 0. Okay, we didn't do it, but also in the previous case when you had all these curves and you had these ones are converging to 0, these ones are moving away. At the point 0, you have, if you remember, x0, e to the alpha t, y0 e to the beta t. Then if x0 and y0 are 0, then you have xt, yt is still a solution, but it's just identically equal to 0, 0 for every t. Okay, it's still perfectly valid as a solution. It just happens to be the constant, for every t it just maps to 0, so that's a 0. Okay, so here also you have a 0 solution. And what does the vectors look like here? Which direction are they pointing in? Okay, they're pointing in positive direction. Okay? And as you get further away, they're getting bigger and bigger, like this, right? And the same thing on this side. Okay? So, what we're looking for now is some function x of t that will satisfy x of t is equal to 3 x of t to the 2/3. The derivative, yes. Okay, so we want a function x of t whose derivative is exactly equal to 3 times the position of x of t. So we would like to take some initial condition and flow it, okay, and find some function that satisfies this. So what I'm going to, the example I'm just going to give is that there exists two solutions. So let's suppose that we want to solve the Cauchy problem, with initial condition x of 0 equals 0 in this case. Okay? So one solution is the 0 solution. Right? So this Cauchy problem. As we said, because we know this vector field is 0, the vector field is 0, but if we take the vector field, the solution x of t equals t cubed, what is the derivative of this with respect to t? X dot of t is equal to 3t squared. And what if,
It's equal to x.
so this t squared is equal to, so x of t is t cubed at each point, okay? So t squared is equal to x of t times the 2 to the 2/3, right? So this is equal to 3x of t to the 2/3, because x of t is t cubed, so if you put t cubed here, you get exactly t squared. So this is an example where you have two solutions to the Cauchy problem, at least two solutions. Both of these are solutions, in the sense that we have two solutions. So there exist two solutions. One is the solution x of t. I actually prefer to put t below. If you don't mind, I'll switch a little bit between one and the other, but x of t is identically 0, okay? And the second solution is x of t equals t cubed. And these are different solutions, they do very different things. If you take this solution here, then this point starts in 0, but as t goes to infinity, it goes to infinity. As t goes to minus infinity, it goes to minus infinity, because this is the position. But the velocity here is 0.
So is this related to the fact that x to the power 2 over 3 is not differentiable at 0?
Yes, it's related to the fact that it's not Lipschitz continuous at 0. Yes, exactly that.
So for maybe the theorem says that it's only Lipschitz solutions.
If it's Lipschitz, then you have uniqueness. Yes. It's not, I don't know how intuitively the fact that it's I don't know. So the derivative is infinity, right? The derivative of the vector field is infinity, right? That's what we mean by non-Lipschitz, right? So x cubed. So if you draw the graph of v, so this is x and this is v, then it will look something like this, right? With infinite derivative there. That's what makes it non-Lipschitz, right? Because the derivative is not uniformly bounded here. And so what does that mean? In some sense, it means that it gets enough charge to get out of here, right? So it really needs to speed up the the function v is in some sense giving it, the velocity is increasing very fast near zero. Whatever, if you want some kind of feeling for why this works. It's as though you're sitting here, your velocity is zero, so you need a really strong kick to get out here.
This actually inspired, so this gave me an idea that 0 for x bigger than or equal to 0 and the other branch for x less than or equal to 0 is again a solution.
Excuse me a second.
So if x is equal to 0 for t bigger than or equal to 0.
Yes.
And for t less than 0, it's t cubed.
Yes, you can, yes, that's a very nice observation, yeah. You can define another solution that is 0 up to t equals 0, and then it's t cubed, or the other way around. Yeah, you can switch from one to the other in some sense at t equals 0. Yes. So this is an example where you lack uniqueness. And then there is the question of the domain of definition. So I am just dedicating one lecture to this, and the proof of this theorem will be in the exercise. It will be an exercise. It will be the main exercise I'd like you to do for tomorrow, because for next exercise session. Because I don't think it's worth spending another hour just going through the proof, or more than 2 hours. But this, of course, there's a lot of theory, and it's a very interesting theory for this, okay? But this is not really a course in ODEs. I'd like to, I could do it more concentrated on ODEs, but there's lots of other stuff that I'd like to do, and we have to choose. We cannot do everything. So I've decided to cut this somewhat short. But let me give you the other example. Is very interesting. Is consider, so again we take just the real line, and we take v of x equals 1 plus x squared. Okay, so the differential equation would be x dot equals 1 plus x squared. So this looks very harmless. It does not look like it's such a complicated thing. So what does this look like? So does this have any fixed points?
0? No, there is no.
Yeah, there's no point where x dot is equal to 0. Okay, so at the point 0, x dot is 1, like this, right? And then as you go larger, it gets bigger. Simple, right? Like 1 plus x squared. And here, it's also going in the same direction. And here, it's also very big, like this. Okay? So this looks like a very simple, like you take some initial condition here, and it just moves along and goes to infinity. In fact, that's what it does. Okay? Dynamically, you start with an initial condition here. It initially moves very fast, because this is its velocity vector. Then it slows down a bit. This is the moment at which it's slowest, but it still has velocity 1. And then it starts speeding up again. Okay. What happens is that it speeds up a bit too fast for its own good.
Isn't the solution for time?
Sorry? Exactly. So the solution, you can easily check that for any initial condition x0, so let's choose some x0, then the solution is xt equals tan of t plus some constant c, which is related to the initial condition, so tan minus 1 over x0. This is a solution. Because that's what you get when you integrate tan. When you differentiate, I'm never very good at this stuff, but okay, here you can see that x of 0 is equal to tan t, right? And this is just equal to x0, right? This is tan t.
Tan c.
Tan c, sorry. Yeah, when t is equal to 0, this is tan c. So if you plug this into here, this is tan of tan minus 1 of x0, which is just x0. Right? So this is the initial condition x0, and the derivative is x dot of t equals, so for those of you who remember these formulas from calculus, which I never remember, it is apparently tan squared. The derivative of tan is 1 plus tan squared, right? And so tan squared of t plus c.
The derivative of tan is tan 6 squared. Tan 6 squared. The derivative of tan inverse is 1 over 6.
Sorry?
Oh, yeah, sorry. My bad.
I can never remember these formulas, I confess. It's my
The
weakness.
derivative of
But
tan
this is what I have in my notes. Yes.
And the 6 squared is 1 plus tan.
And so this gives, this is 1, so this is 1 plus tan t plus c squared. That's what tan squared means, right? And this is just xt. So this is equal to 1 plus xt squared, which is exactly the condition we want, right? So x, the derivative of x of t is equal, this is exactly equal to v of x of t, because this is v of x. So this shows that this is a solution, okay? Now, what domain is this solution defined on? So we start with, at time t equals 0, we are in x0, okay? And what happens as t goes to infinity? It cannot go to infinity. Why not?
Because it's not defined.
It's not defined.
everywhere.
Exactly. So what happens to tan? What happens to tan? What is the graph of tan?
It has to stay within an interval of
Exactly,
0 to,
exactly.
5 and
So
5
the,
over 0.
the tan is
Between minus pi half and
3 minus pi and pi over 2 or minus pi
pi
over
half.
2.
something like this, I think, right?
Yes.
And then it repeats. Okay, something also like that. It repeats. But the point is that if you now take from t, yeah, we're only really interested in this because we're not. It depends on c. Let's pretend for the moment that let's simplify and take x0 equals 0. Okay, and then we just take xt. So for c equals 0, we have xt equals tan t. It's a little bit simpler. So we suppose that our initial condition is here. Okay. So what is the evolution of this point? Where is x? So where is x of t? As t becomes positive, so t is equal to 0, x of 0 equals 0, and then x of t is here. So this is t, and this is x of t. And as t approaches, what is this? Pi over 2, right? As t approaches pi over 2, what happens to x of t? It's going to infinity. Yeah. So what does that mean? That means that this
Accelerates very much.
is accelerating so fast that it reaches infinity in finite time. In other words, as t approaches pi over 2, xt tends to infinity. So this tends to infinity as t approaches pi over 2.
And this is obvious from the differential equation because the far it goes, the more velocity it gains because now x becomes great.
Intuitively, again, these are intuitive like before, you get a feeling for why it's happening. In some sense, intuitively, it's because it's going too fast. But technically it's just because that's how the formula works.
But from the formula, it doesn't. We can't say that it goes too fast.
When you look at it like this, you have no idea.
Yes.
When you look at it like this, that's what I was saying at the beginning. You look at this, it looks innocent enough. It's simple, right? All you're saying is that the velocity is x squared. But x squared goes to infinity quite fast. And
But not in a finite interval.
no. X squared is just x squared. X squared just says, but what I'm saying is that x squared means that actually the velocity is very large. X squared is a very large number. When x is large, x squared is very large. Whatever. We don't need to use a heuristic argument because this is what the calculation tells.
So I have a question.
Yes.
So suppose we're starting from an interval where it's
So we're saying take a solution that starts in x0. So geometrically the solution will go to minus infinity and plus infinity. It's just the time, the domain of definition of that solution. Okay, so let me just write here, for example. So this goes to minus infinity as t converges to minus pi over 2. Okay, so the conclusion of this is that okay, so in that particular case, for all initial conditions x0 and r, there exists solution there exists a solution defined on so there exists a solution x from I into R where I is equal to minus c minus pi over 2 c plus pi over 2. This should be over.
Not be minus c in both cases. Maybe?
You're right. Thank you, yes. Yes. Yeah, so C is the initial condition, and it is, yes, it is a domain. C is the center when t is equal to 0, and then t can go to minus pi over 2 and plus pi over 2 minus c. And this solution cannot be extended. Cannot be extended. But notice that x of the whole interval I is equal to r, right? So geometrically, when you look at the range, the domain of the solution is the whole real line. So this is now a map that maps this interval here into the whole real line. Okay? So this is another source of confusion because sometimes this is referred to having a global solution, or whenever in the differential equations you talk about a global solution, we're talking about a solution defined for all time. It has nothing to do with what the solution looks like in your space. Okay? Because even a solution that is just always identically 0, if you have a fixed point, it's defined for all time on the fixed point, that's still a global solution. Okay? So global solution has to do with the fact that it's defined for all time. So in these cases like this, we do not get a flow. Okay? So this, because of this differential equation does not give a flow because we do not get, in these examples, in these cases, we do not get a flow, right? In the sense of said before, of a continuous time dynamical system. because this is not defined outside. You take an initial condition and you try to sorry, I should have sorry, there's a sentence I want me to say before this. Any questions about this? Is this okay? Okay. So now let's look a little bit back at the,
I just have a question.
yes.
Why can't we extend this? If we take another branch of the TAM, the resulting function also satisfies the same differential equation.
Well, but the solution has already gone to infinity. I mean, how are you going to...
As a differential equation, this new function also satisfies the
Extend all domain?
I mean, we just take this interval and this interval and excluding the point in between, because the function is not even continuous at this point. And this function, this new function, is an extension and it satisfies the same differential equation with the same initial condition.
It is not same.
So we would like I to be an interval, right?
We would like I to be all of R.
No, I mean we don't want it to be any set. Could be.
It needs to be a connected set, you
Yes.
mean? Yeah, what you're suggesting would give I to be two connected sets. I don't know, I have to think about that a little bit, but if, how would you even define the new, how would you define xt in your new,
I will just
in your
take
set?
the TAM branches, all of the TAM branches excluding the multiples of pi over 2. I can define a function over all R except the multiples of pi over 2.
Yes, but that would not be so. No,
That's why I'm excluding the pi over 2 points.
Because it's not continuous around.
No, it is continuous over R minus multiples of pi over 2.
No, because when you approach it,
Yes,
both
but these
sides
points
go-
are not in the
yes, it's continuous at every point that is not that. But I don't know how to exclude that case. Maybe I mean maybe I'm not sure. I mean, as you said, it still does not give you a flow. It still does not give you anything. Maybe it can be useful in some setting, in some context, yes. But certainly you want I to be an interval, yes, as you said. You want I to be connected subset of R. Yes. So if the the connection with the flow is that if x dot equals v of x, has a unique global solution for all initial conditions in your space, so for all initial conditions x0 in our space, let's say Ln, then it defines a flow. i.e. a continuous time dynamical system. How does it define a continuous time dynamical system? So we have our space here, okay, and we have a differential equation in this space, x dot equals v of x, and suppose we in a moment I'll give the theorem that guarantees when this is true, but suppose that through every point, through every initial condition, x0, by which I mean x0, y0, right? There is a unique solution, and this unique solution is defined for all time. Okay? Then how would we define a flow? So we want to define a flow, which is, as you remember, one parameter group of transformations, T in R. Okay? Well, it's easy how to define a flow, right? Because we just take for each, so we want to define Ft of x0 is just equal to xt, where xt is what you get by looking at the solution of the differential equation through x0, right? So you define this map F that gives you, at every point at time t, it gives you the position of that time after time t under this differential equation. So at some point here you get xt, and this is how you define the flow. Okay, let's just take a 3-minute break. Okay, before we go on this. Thank you. Stretch your legs, get a drink of water, whatever. You came in right in the deep end. So, the theorem that's in the exercises is the following. Theorem. Let V Rn to Rn be a continuous vector field. Then for every x0 initial condition in Rn, 1, there exists a local solution. So by local solution mean just some I, right, for some interval of time. There exists a local solution x I into Rn with x0 equals x0, x of 0 equals x0, so for the Cauchy problem. 2, if V is locally Lipschitz, then this solution is unique. And 3, if V is Lipschitz, then it is a global solution. And in case 3,
What do you mean by global solution?
yes, I will say a second. In case 3, the solutions depend continuously on initial conditions. Okay, so let's make several comments, let's discuss a little bit this. What is this? So I think the exercises, I'm not sure if the exercises contain the proof of 1. The exercises contain the proof in the locally Lipschitz, or maybe just in the Lipschitz case. But let's discuss all these various cases. So the fundamental theorem, this is sometimes called the Peano theorem, is that as long as it's continuous, there always exists a solution, which is really quite remarkable, actually. When you think of it heuristically as that you just have this collection of vectors all over the place, right? So you have these vectors, they depend continuously, so it cannot be too wild. This is your initial condition, says they exist at least in some neighborhood, a little solution. Or it can even be like everywhere, but the time, what you know for sure is that the time might not be defined for all time. Now, if V is locally Lipschitz, what does locally Lipschitz mean?
Lipschitz, but
There is a neighborhood in which it is Lipschitz.
Yeah, so it means it's Lipschitz in a neighborhood of this, but over the whole space it might not be Lipschitz with the same Lipschitz constant, right? So the example we had before, is this Lipschitz or locally Lipschitz? This is locally Lipschitz, right? Because the derivative is unbounded, so the Lipschitz constant is unbounded. And that's what gives the problem of the global existence here, right? So the solution is unique. So locally Lipschitz is just defined because the first counterexample was not even locally Lipschitz at 0. Right? The example we showed where we did not have uniqueness of solutions, remember x to the 2 over 3, the derivative was infinity at 0. So in a neighborhood of 0 it was not even locally Lipschitz, it was continuous. So it had a solution, but this solution was not unique because it was not locally Lipschitz. This one is locally Lipschitz, so it has a unique solution, but it's not globally Lipschitz, so the solution is not a global solution. Global means that I is equal to R. It means that the solution is defined for all time. That's what a global solution is. A local solution means that it's defined in some interval containing 0. So the conclusion from what I did not give a formal proof of that. Maybe I'll try to write down an exercise for that because I think it's relevant. Whenever you have a global solution, you have a flow. Whenever you have this, whenever it's Lipschitz, which means that through every point there is a unique global solution, okay, then you have a flow. You have a continuous time dynamical system because for every point you can just define f of t to be the image of that point on the time t, so you get a flow. Okay? Depend continuously and you get a flow. You have and it defines, and the equation defines a flow. Wait, there was something else I wanted to say. Yes, the continuous dependence. This is another thing that can create a little bit of confusion. And I want to say what exactly we mean by continuous dependence on initial conditions. You know what?
Also by continuous vector field.
Excuse me?
Also by continuous vector field.
What we mean by continuous vector field is just a continuous vector field. Remember that a vector field is just a function from Rn to, it's a map from Rn to Rn. So it's continuous.
Continuous dependence is like the small change of x is make the small change of function of x.
Yes, so what exactly do we mean? Because that's true, of course, continuous depends on initial conditions, means if you choose an initial condition nearby, then the solution is nearby. Is that what it means?
But under what kind of metric for the functions? The supremum or?
Well, okay, so exactly, let's be a little bit more precise. Let's look at the example we had before, where we had this differential equation, right? This linear differential equation. So let's look, for example, at an initial condition here and an initial condition nearby here. So if I take an initial condition here, we know that this converges to 0. This was the example, right? But this initial condition, it goes all the way here. So what kind of continuous dependence is that?
At D.
Sorry?
At each T.
At each t, exactly. Okay, this is just a little subtle point. It's important to realize that. So what we mean for the continuous dependence on initial condition means that if you fix t, so continuous dependence on initial conditions, what this means is for all t, let's say greater than 0, there exists epsilon greater than 0, such that if x0, if the distance between two initial conditions x0 and y0 is less than epsilon, okay, let's do it. For all epsilon, there exists delta, okay, such that if this is less than delta, then the distance between xt and yt is less than epsilon. And does that hold in this example here, using this example here?
Yes, of course, because I can take this point such that this curve becomes more tangent to the y-axis.
That's right, because if the closer you take it here, and the more it does this, right?
Yes.
So if I take the delta very small, then I can stay close to this as long as I want. Okay, by taking some point that is very, very close, I can really come very, very close here. Okay, but so this is just a little subtlety, like this. I think this field of differential equations, at least the basic definitions, are full of these little subtleties. You know, exactly what do we mean by x dot equals vx and so on, and also this continuous dependence on initial condition is very tricky. You have to be careful. It really means. It cannot mean, if you think about it, that the solutions stay together for all time, stay close. There are some cases when it does that, but there are many natural cases in which it does not, like this. Also, you can take 2 points even on either side of this. One goes here and one goes here, but they can be arbitrarily close, right? But in finite pieces of time, then they depend continuously. Right? That's really the reason why I'm talking about this happening here. I mean, in some sense, this also happens here, but here it's a bit more delicate because the solutions are not defined for all time. In some places they are, in some places they're not, so it's not completely obvious how to, maybe in some cases you still have continuous, but you need to give it more meaning. But in this case, then it's always the case that it's like that. For each time you have that situation. The final remark maybe also is just to notice that both in a flow and in this case when you have global solutions. So geometrically, so the example we saw of the non-uniqueness of solution is not geometrically very obvious because it was just in the real line, right? We had the x equals 0 and x equals t cubed, okay? But geometrically, what would it be? I did not prepare a specific example, but geometrically, what this could mean in 2 dimensions is that you have a point here through which you have non-uniqueness of solutions like this, right? So you have one solution coming like this, and then you have another solution coming like this. So they go through the same point, right? They both have the same tangent vector. So here you have your vector field. Here you have a vector field like this. So everything is completely consistent. So there are 2 curves, maybe tangent at this point, and so in principle, through that point, you might have 2 or many different solutions, and this case happens. Okay, and when you look at it like that, in some sense, this theorem becomes much more remarkable because it is if you just have this bunch of vectors everywhere, there's not really any reason why you should expect this to be a situation that doesn't occur very easily. You know, you take a curve through here that is tangent here, and then you have lots of vectors in different positions, right? How should you know that there can only be one way to continue this curve, tangent to every vector field, right? There's no reason why it should. And in fact, if it's not Lipschitz, it might not be the case, okay? But if it's Lipschitz, then the uniqueness of the solution means that through any 2 points, you never have 2 solutions going through the same point, okay? And this has a kind of, geometrically, it has a significance when you're studying what can happen, because sometimes you can look at the structure of the solutions and the fact that you know, for example, you may have a periodic solution here, and then you know that a solution that starts in here can never leave here, so there's consequences to the fact that 2 solutions can never cross. So I've done these 2 lectures really talking about continuous time dynamical systems and the fact that differential equations are essentially the main source of continuous time dynamical systems. But having done all this, we're not really going to do any more continuous time dynamical systems, because a lot of the formalism, as I said before, the omega limits, the periodic points, so a lot of the concepts and the definitions and many of the results hold for discrete time dynamical systems and for continuous time dynamical systems. But discrete time dynamical systems are much easier to study. Okay? So in this introductory course, when we're trying to introduce some fundamental concepts, it makes much more sense to introduce them and to study them in the context of discrete dynamical systems, which is what we're going to focus on for the rest of the course. But I wanted to give these because in real life, in other fields, in geodesic flows, in many other fields, in differential equations, continuous time dynamical systems come in, and I wanted to make sure that you saw that it's really the formalism is, you know, that the connection between discrete time and these kind of systems. Okay, that was the purpose. Okay, I think we can call it a day for today. Thank you very much.